Good morning everyone. So today we are going to start the last topic of Fourier series, which is Fourier sine series and Fourier cosine series. So to begin with, let's recall the concept of even function and odd function. So we say that f of x is even if f of x is equal to f of minus x. For example, x square and cos x are even function. F of x is odd if f of minus x is minus f of x, that is x cube and sin x are odd functions. So now let f of x be integrable over the interval minus pi to pi, and if f of x is even, then its Fourier series has only cosine terms, because if you compute an, then an is 1 by pi minus pi to pi, f of x is even and cos nx is even. Even is even function. So since this is an even function, therefore its integral over the interval minus pi to pi would become 2 by pi and 0 to pi. But in the second case, when you compute bn, then this is an odd function. F of x is even, sin nx is odd. That's why integration from minus pi to pi would be 0. And that's why it would have only cosine terms. Similarly, if f of x is odd, then you can see that this is odd, this is odd. So odd becomes even. So this is odd, this is odd becomes even, and that's why bn is 2 by pi 0 to pi. But in case of an, it would be 2 by pi 0 to pi f of x cos nx, which is odd, and that's why it becomes 0. So it means that if we have the information of the function that over the interval minus pi to pi it is odd or even, so based on that we can directly consider either an to be 0 or bn to be 0. So let's compute the Fourier series of f of x is equal to x and f of x is equal to mod x. You can observe here that, please do try to solve it by yourself. And the first thing to observe here is that f of x is equal to x is odd, which means an would be 0, and f of x is equal to mod x is even, which means bn would be 0. So f of x is odd, therefore a naught an is 0, and your bn would be 2 by pi 0 to pi x sin nx dx. That gives you bn to be 2. Try to solve it by yourself, very simple integration is there. And that gives you x is equal to 2 sin x minus sin 2x by 2 and so on. Similarly, if you consider, yes, when one very important point is that when you write x is equal to 2 sin x minus sin 2x and so on, now here if you put x is equal to pi, then the left hand side would be pi but right hand side would be 0. Similarly, for minus pi, left hand side is minus pi but the right hand side is 0. It means that this series is not converging at the end points, which are the point of discontinuities, and therefore we define it as x is equal to 2 sin x minus sin 2x by 2 and so on over the open interval minus pi to pi. So in case of sine series, always remember that at x is equal to 0, pi and minus pi, it always converges to 0. So if the value of the function is 0 at these points, then it's okay. Otherwise, to be on the safe side, we always consider the open interval minus pi to pi. And at 0, we may need to redefine it. In this case, we don't have to define, because left hand side would be 0 and the right hand side would be 0 at x is equal to 0. If I consider f of x is equal to mod x, it is even, therefore bn is 0, and I can directly compute a naught and an using the property which we have discussed. So minus pi to pi would become 2 by pi, rest would remains as it is, and therefore this is how the series looks like. So in the first case we get only sine terms, and in the second case when it is even function we get only cosine terms, where the x belongs to the closed interval minus pi to pi. Okay, now the quick observation is that if I consider the function, if I let's say I consider the function f of x to be x over the interval 0 to pi. So in this case both the functions are same, x also and mod x also, both becomes x. Yes, it means that over this interval 0 to pi, the first series which I got can be called as the sine series of x, and the second series I got can be called as the cosine series of x. Other way around, what exactly has happened is that let's say the question is for fx is equal to x, find its sine series and cosine series where x belongs to open interval 0 to pi. So to find its sine and cosine series, you have to rewrite f of x as odd function over the interval minus pi to pi and as even function over the interval minus pi to pi. Yes, so when you have to write it as an odd function over the interval minus pi to pi, you consider f of x is equal to x, that gives you sine series, and you write mod x, that gives you cosine series. So this is very important concept. This is how we write the sine series and the cosine series. We have given over the interval 0 to pi, we extend it. If I need the sine series, then I extend the function in such a way that it remains odd. If it is, I have to write down the cosine series, I extend it in such a way that it becomes even. Yes, so this is the information, and that's why we consider this example. So now I can say that f of clearly mod x is equal to x for x greater than equal to 0, and the series 1 and 2 are expansion of f of x is equal to x over the interval 0 to pi. One is called Fourier sine series and 2 is called the Fourier cosine series for x. So similarly, any function that satisfies Dirichlet condition can be expressed in both sine and cosine series for the interval 0 to pi, such that the sine series cannot converge to f of x at endpoints 0 and pi. It only converges if its value is 0 at these endpoints. So to obtain the sine series, we redefine the function to have value 0 at x is equal to 0 and then extend it over the interval minus pi to 0 such that the extended function is odd. Similarly, for the cosine function, we extend it so that the extended function remains even over the interval minus pi to pi. And why we are extending it? Because the formulas which we have obtained for a naught, an and bn works over the interval minus pi to pi. So that's why if we have given the interval 0 to pi, then we cannot directly use the formulas for a naught, an and bn. So we are extending it over the interval minus pi to pi, and then using the properties of the odd function or the even function, we are obtaining the sine series or the cosine series. Let's see an example. So find the sine and cosine series for f of x is equal to cos x, where x belongs to 0 to pi. Yes, now f of x is equal to cos x, it's an even function. So if I extend it over minus pi to 0, I keep it as cos x, so it remains even. But if I have to make it odd, then I will define from 0 to pi, it's already defined cos x, and if I define as cos x from minus pi to 0, it remains even. Therefore I define it as minus cos x from minus pi to 0. So this is how the cosine series and sine series looks like. Cosine series is a naught by 2 plus summation a n cosine x. Sine series is summation b n sin n x. And these are the formulas. A n is 2 by pi, 0 to pi and so on. Similarly, a naught and b n can be computed. Yes, so these are the direct formulas. Now for the sine series, redefine the function f of x is equal to this one. Yes, you can quickly verify that it is odd. There can be many ways, but one way is that let's say your f of u is cos u and 0 is less than u is pi and minus cos u. So now if I replace u by minus x, then it becomes cos of minus x, which is cos x, and minus cos of minus x, which is minus cos x, But here what will happen when you write 0 less than minus x is less than pi, so this is same as minus pi less than x is less than 0, because it is minus x here. And similarly in the other case you will get 0 less than x is less than pi. So now you can see here that for 0 to pi it is cos x, but f of minus x is from 0 to pi minus cos x. Similarly from minus pi to 0 f of x is minus cos x, and here it is minus of minus cos x. So therefore clearly f of minus x is minus f of x, and this is why it is an, we redefine it so that it remains the odd function. Now since it is an odd function, now I can use the formulas. So clearly an would be 0. I am not going into the detail of computing bn, I have written it. You can verify by yourself. It comes out to be b2n minus 1 is 0 and b2n is 8n by pi for n square minus 1. Here one observation is that when I computed bn, then it comes out to be n minus 1 and plus 1. So if I put n is equal to 1, then it is not defined. That's why I clearly mentioned that n is greater than 1. It means that I have to compute b1 separately. So if I compute b1 separately, it comes out to be 0. And now I substitute the value. So sine series is cos x is equal to summation bn sine nx. So only b2n has the values, others are 0. So I substitute these values, and I clearly mentioned here that over the open interval 0 to pi, because you can see that cos pi is minus 1 and cos 0 is 1, but the left hand side at x is equal to 0 and x is equal to pi, it's 0. So that's why I consider the open interval 0 to pi. Now for the cosine series, f of x is equal to cos x, it's already even, so I extend it over the interval minus pi to pi, and cos x itself is a cosine series, so therefore cos x, the cosine series of cos x is cos x itself. Here I should mention the interval minus pi. Okay, let's try one more question which says that find Fourier cosine series for f of x is equal to x sine x, and hence find the value of this sum. So I just need the Fourier cosine series. Now I can see that x is odd, sine x is odd, odd becomes even, so it's already an even function. Therefore I can easily extend it over the interval minus pi to pi, it remains same. So fx x, so redefine it as x sine x over the interval minus pi to pi. So I need the cosine series. I compute a naught and I compute an. Again in the an, in the denominator I will get n minus 1. That's why I have to compute a1 separately. So I clearly mentioned n greater than 1 when I computed an, and then I compute a1 separately, which comes out to be minus half. So this gives me the required cosine series of x sine x. Yes, please do verify your answer. Now the problem is that I need to find the value of this sum. So it means you need to find an appropriate value of x where x sine x or the series is converging to x sine x. This is very important, and you will get this sum. So think what could be the appropriate value. If I choose x is equal to pi by 2, then the left hand side would be pi by 2 and the right hand side would be 1, and cos pi by 2 is 0 and cos n pi by 2. But here you should mention that x is equal to pi by 2, f of x is continuous. and therefore the series converges to f of pi by 2, which is pi by 2, and that is why you can write the left hand side to be pi by 2, because it is f of x is continuous at this point. So now cos n pi by 2. So cos n pi by 2, it means that when n is 1, it is pi by 2, which is 0. When n is 2, it is minus 1. For 3, it is 0. For n is equal to 4, it is 1. So minus 1, minus 1, 1. So it means that for the values 2n, which means 2, 4, 6, 8, the values are 1, minus 1, and for rest it is 0. So that's why replace n by 2n, and you can see that if you substitute the different values, alternatively you get plus minus. So that's why I replaced n minus 1 as 2n minus 1 and n plus 1 is 2n plus 1, and the left hand side I take minus 1 to that side, and that gives me the value of the sum which I am looking for. So the last topic is extension to the arbitrary intervals. So let us assume that f of x is defined over the interval minus L to L. In this case, if I have to find its Fourier series, then I have to define another variable which gives us, let's say, t, such that t would vary from minus pi to pi, so that I can use the Fourier series, or I can obtain the Fourier series for that function of t, and then I replace back it in terms of the x. So let t is equal to x pi by L. Yes. So when you define t to be x pi by L, clearly t varies from minus pi to pi. It means you can write f of x as f of Lt by pi, which is g of t. Now for the g of t, you can easily write down the Fourier series, and in that Fourier series again you put back the value of t, which is x pi by L. That gives you the required Fourier series of f of x over the interval minus L to L. So this is your g of t, and then you compute f of x, and technically over the interval minus L to L, this is how the bn and an looks like. So as I told you, let's see an example where f of x is defined over the interval minus 2 to 2. It means L is 2. So you define t to be x pi by L, where L is 2. That means t is x pi by 2 and x is 2t by pi. So now g of t, since f of x both the values are constant, there is no x, so therefore it remains same, 0 and 1 over the interval minus pi to 0 and 0 to pi. So we quickly compute a naught, which comes out to be 1. An is 0, it's a constant function, and bn is 1 by n pi, 1 minus 1 raised to the power n, which means b2n is 0 and b2n minus 1 is 2 by 2n minus 1 pi. That gives me required g of t. Now in the g of t, I put back the values in terms of x. That gives me the Fourier series for f of x over the interval minus 2 to 2. And this series converges to periodic extension of f of x. Now the period is 4 instead of 2 pi at all points except the point of discontinuity. So you can see that at 0, at plus minus 2 and plus minus 4 and so on, it has the jump discontinuity. And at these values, using the Dirichlet condition, you can find that you need to redefine the function whose sum is 1 by 2. So that's all from today's class. Thank you.